Welcome to another STEM communication at TSP Online Schooling and Coaching Program. Today we are looking at another STEM subject, which is physics, and we are looking at dimensional analysis. Part 5, Part 5C. We have looked at Part A, B of this particular usefulness, importance, or significance of dimensional analysis, which is establishing connectivity in formula or equation of physical quantities. How physical quantities in STEM are being connected in terms of formula, some of which we have been using from the time we start schooling. And today we are looking at this part C because there are so many dimensions, so many insights into how problems can be solved in establishing this connectivity. And there are some mathematical relation and idea or truths that I need to bring across the learners. That is why I classify them into three: A, 5A, 5B, and 5C. So this particular one, I have two problems for us to address, and you will see that the techniques, the strategy of solving this particular one is different from the one that we have done in the previous two editions of this particular aspect of dimensional analysis, 5. So you are going to see some kind of insights and thinking which I'm going to bring on board. So we have problem 1 and we have problem 2. We will start with problem 1 and I'll try to explain one or two things clearly. Now problem 1 says the distance covered by a body in time t is given by the relation x, which is distance, okay, the distance x, okay, take note of that, the distance x, maybe I should put it there, the distance x, okay, now, covered by a body in time t is given by the relation x equals to a plus bt plus ct squared. Number 1, state the dimension of A, B, and C. 2, define A, B, and C. Take note of that. Stating their base units. Okay? Then number 3, what is the difference between A and distance? Oh, that is interesting. That means we need to know what A is from this equation, from this relation, for us to be able to differentiate between A and distance. Now, before we go into this, I want to quickly explain some stuff for you in mathematics. Now, in the previous edition, I tried to make mention of it, but I'm going to be more clearer here. When you have 2 or 3 terms or variables being joined together by plus and or minus, subtraction, addition or subtraction, is different from multiplication and division. Now in mathematics, don't forget, at this platform, our interest is to use real life relational teaching techniques, meaning to relate content, abstract content, imaginary content to your real world so that you're able to see. And you will notice that most of these things that we do in science are reality. They emerge from reality. They may be invisible reality coming to existence in the physical. And so you will notice that these first two, addition and subtraction, are connected. Now, when two things are connected by addition and subtraction, okay, it is bond, very strong bonding that exists between them. Very strong bonding. If two things or more are joined together by multiplication or division, this one is strong bonding. This one is also bonding, but it is weak bonding. Now, what do I mean? Now, when you say things are being joined by addition or subtraction, this can be likened to marriage, relationship, marriage, the bond is very powerful. And so when you have two things, say A and B, what it means in reality is that for them to have been bonded, they are the same. It means that this A is the same thing as this B, either plus or minus. Take note of that. That means for them to have been adjable, it means they are from the same source. They have become the same source, or they are from the same source. For example, naira can be added with naira. Dollar can be added with dollar. But you cannot add naira and dollar together except you make conversion plus. So the moment I say naira plus naira, it means naira is the same as naira. That's why I'm able to add them together. If I say dollar plus dollar, it means dollar still remains as dollar. So if I say A plus or minus B, it means A is the same as B. Take note of that. I'm going to use this concept here in solving this problem, and to make our work a whole lot easier. What will have taken us like 20 minutes, 30 minutes, will take us just 2-3 minutes to solve with this now I'm explaining. But when it's multiplication and division, that is ordinary friendship or moment of courtship. There has not been any bond. There has not been any vow. There has not been any commitment. And so if you have two things being together by multiplication, A times B, AB, or A divided by B, you cannot say that A is equal to B. No, you can't say that. Because if I make one to be 0, the other one will not exist again. Because it's just weak bonding. It's ordinary fellowship, ordinary friendship. If I make anyone to be 0, everything will become 0, non-existent. Unlike this, if I make any of A and B 0 in addition or subtraction, one will still be in existence. Do you understand? But for multiplication and division, they will disappear or they will become infinite, not existence. So take note of this as I use this thinking in solving one or two problems here. So most of these things that we do in mathematics, they have real life application. Addition is very strong bond, very strong bonding, not weak one. Multiplication and division is weak bonding because they can disappear. They can come into non-existence. Now let's solve this. So it means that if you look at this, for x to be equal to a plus bt plus ct squared, for what I just explained now, it means that, look here, it means that this x is equal to a, this a is equal to bt, this bt is equal to ct squared, and this a also is also equal to what? Ct squared, because by the virtue of being joined by addition, that means they have something in common. That is the meaning. If they don't have anything in common, you cannot say plus. So that means I can write this like this. Please take note. I'm going to use this concept to solve this problem. Now, they said that we should state the dimension of A, B, and C. Now, don't forget that X is. Let's start with number 1. With number 1. Okay? A. I want to find A. From here, you can see that A equals to X. And what is X? X is distance. Distance is dimensionally is length. So we have not A to be this. Okay? Let me bullet this. Now, for me to get B, A plus B, A equals to what? BT. I already know A to be N, so I'll put N here equals to B. Okay? This T is time. This dimension is capital letter T. So from this, if I make B simple as the formula, I will divide both by T. My B becomes L over T, which look like either speed or velocity. Then the third one, I need to find my c. Now, which one do I use now? I can use any of this. I can use this. You will recall that a also equals to ct squared. A is already L. I put L here. Okay? Equals to c. That's what I'm looking for. I put that c there. T is time. This dimension is capital letter T. Capital letter T squared. Which implies that I can find my c by dividing both by t squared. So that will be L over t squared. Can you see that? Now, that is acceleration, meter per second squared. So it means that the line length upward, because it is from this must definitely is not speed, it's velocity. Because for acceleration to exist from this, it means this is velocity. Then it means that this one is not distance, is displacement. Because it is displacement over time that gives us velocity. So there is nowhere ordinary distance or ordinary speed comes out here. So the same should state the dimension of this. So you can see the dimension of A is L, that of B is L over T, that of C is equal to this. This is equal to C. That of C is equal to L over T squared. That answer number one. Number two, let's define A, B, and C, stating their base units. Do you see that? Okay. Now, let's see what they are expecting us to do there. Okay, let me just clean this and then reduce it. Sorry about that. So, we have this like this. Okay. So, now, define A. So, we have seen that A is displacement. That is distance in a specified direction. That is the definition. B is velocity. Change in displacement or rate of displacement. The rate of displacement is velocity. Then acceleration is the rate of velocity or change in velocity per time. That is acceleration, C. Now, the same to state their base unit. The base unit for displacement is still meter. Don't forget that. The base unit for velocity is meter per second. Then the base unit for this acceleration, length is meter, time is second, so per second squared. Do you see that? Then the third part says, what is the difference between A and distance? Now we now understand now that A is actually displacement and distance. What's different? A is vector quantity, distance is a scalar quantity. That's a major difference. That means A has both magnitude and direction, while distance only has magnitude, no direction. I hope you have been able to understand. See the way I solve the problem. If you should attempt this in another way, you may be right, but it will take you a whole lot of time. Okay, now let me clean this so that I can solve the second one, which will be much more interesting because of things that are coming right from there. Now, look at this. Look at this number 2. In an equation, P plus A over B squared in bracket times, because when you have two brackets joined side by side, it is times V minus B equals to nRT. P is pressure, V is the volume, T is the temperature, and A, B, and R are constants. Then there are some questions they want us to solve. Now let me quickly explain this. Just like when I started this particular communication, I think that for this P to be added to this A over B squared, it means they have the same dimension. They are the same. It means that this P is equal to what? A over B squared. That is why there is a plus between them. You need to take note of that. You cannot add two things if they are not of the same dimension, if they are not of the same source, if they are not equal. So it means that the first thing I will write out from that place is this, is that P plus a over v squared to have existed, or to have exist, it means that p is equal to a over v squared. Please take note of that. Again, v minus b, I told you both plus addition and subtraction, it means bonding. The only difference between the two bonding is that this one is a stronger bond. This one is strong also, but less compared to what? Plus, because less means reduction. But they are the same. It means that for v minus b to have exist, for them to have been combined with this subtraction symbol or sign, it means that v is also equal to what? B. And then now these two in brackets means times, because what separates this and this is multiplication. So this one, this two is equal to what? This. It also means that these two, if you multiply these two and this one together, it will give you nRT. Take note of that. Now again, it also means that this one now, we can represent this to be just ordinary x, and this one can be represented as ordinary y. Okay? So it means that in that case also, xy is equal to what? nRT. Please take note of this. Now let's go ahead to solve this problem now. The first question here is that what is the dimensional formula of a over b? Now what can make easy? To get a, I can get a from this. From p is equal to a over v squared. And they have told me that P is pressure. Pressure is force over area. I'm looking for A. V is volume. Volume is L cube. Then you square it. Because V squared is what we have there. Now, force is mass times acceleration over area is L squared. You know that already? Then equals to A divided by, now law of indices, exponent multiply exponent, that will be 3 times 2 is 6, L is plus 6. Now you come back here, M is mass. The symbol for mass is capital letter M, dot G is acceleration due to gravity, that is L over T squared, you remember? Then we have over L squared here, let me put it here, over L squared. B equals to, don't forget we are looking for over A, we don't know what A is. Then over what? L is power 6. Now, we are looking for A. So all you need to do is to bring this together and cross multiply for you to get your A. So what do you have there? 1 L here, 2 here, so this will reduce to 1, capital letter M over L. Then dot T square here. B equals to A over L raised to power 6. If you cross multiply, you are going to have A dot L dot T squared. B equals to this times this. That will be M dot L raised to power 6. If you cross multiply like this. This come here, this go here. Now I'm looking for A. I will divide both sides by this. So my A now becomes M over L raised to power 6 divided by this. L dot T squared, which gives me this as A. Look at it. A becomes, we have M here. Do you see that? 6L up, 1 down. That will be L raised to power 5. Because, okay, then T squared down. If you take that T squared up, it becomes, or just leave it like this, that will be T raised to power 2. Okay, that is our A. Now, again, we need to find B. I want to clean this up. Now, if I clean this now, I will get my B. Okay? Now, my B, let's see. Can we get it from here? V equals to B. V is equal to B. And V is volume. That is L raised to power 3. So that means my B now is this, dimensionally. Now, the first question says I have to find, Roman number 1 says I have to find A over B. It simply means this M L raised to power 5 over T squared. This line is divided by B. B is this now. L raised to power 3 over 1. Then I will change this to multiplication. It will be m L raised to power 5 over t squared times 1 over L raised to power 3. So this is m, okay? Now, this one we have 5 of L here, 3 here, to cancel the remaining 2 up there. Law of indices divided by t squared, which can be written as m L squared. I take this off, that will be t raised to power minus 2. That's our A over B, that is symmetry R dimension. So A over B dimensionally is this. Mass for M, L squared for L for meter, then squared, then T for time, per time squared. Okay? Now, that is that. Do you see how the techniques for solving this? If you should attempt to say, okay, you want to open up the bracket and find this, I bet you may spend 30 minutes, 40 minutes, 50 minutes to solve what you can just solve. So in the techniques I just brought in, the idea, the logic, the thinking, make it easier. And once you understand this in mathematics, you get a lot of work that looks so complex being done within a twinkle of an eye. Okay? Now, so let's go to the next one. So we have our B now. Our B is equal to m L5 over t. What do we get the other time? Is it t squared now? T squared, yes. Now, the second part of that question says, derive the dimension and base unit of the gas constant R if n represents amount of the gaseous substance. Don't forget, amount of substance is one of the fundamental quantity, okay, whose unit is mole. So the second you find this out. Now you will recall that I told you that this one by definition is this P plus A over this one is simply pressure. So this is pressure times this V minus B. Since this is volume, this B is also volume. So this is times volume equals to nRT. That's the thinking. Okay? So we are looking for R. I will divide both by NT. So my R now is pressure P times volume V divided by NT. So with this, we can derive the unit. Okay, I want to derive the unit in terms of Newton. I want Newton to come up here. Okay. Now, this pressure is force over area. Dot. This volume is L cube. This, okay, that's volume over N dot T. Temperature is already in the basic dimension. Force is mass times acceleration, but I want to leave this one as Newton, okay? But this one is meter, that's going to be Newton, the unit there, okay? Dot area is meter squared, okay? This volume, that is V, is meter cube, because they want us to find the base unit, so I want to go straight. Then temperature is degree Kelvin. Then we have another one here, N is mole. Okay? So now we have Newton. This M, we have 2 M here, meter, 3 here. So one will be one up there that remain here, divided by degree Kelvin dot mole. Okay, which can be written as Newton meter. Now I take this up, that will be per Kelvin, then per mole. If I take this up, do you understand that? So that is the unit. So if you like, don't forget that this one can be further broken down to base unit. Newton is mass times acceleration, so you can decide to do that. But let's just leave this the way it is now. Now, so that is the SI unit for this gas constant R. Okay, can you see that? Now, let's go to the third question. It says, show that, yeah, that can be very interesting. That can be very, what I'm saying there can be very interesting. You see that we should show that nRT N out equals to work done. That we should show that N out is work done. Okay? Now, we just finished that that is number 1 minus 3, capital letter 1 minus 1. We want to show that NRT equals to work done. Work done is force times distance. Work done is force times distance. Work done is also, work done, look at it, is force times distance. It is also equals to pressure times change in volume. It's also equals to pressure times change in volume. That's it. So, in a simple way, nRT is equals to P delta V, which is the same thing as the equation given to us. Can you see that? This is pressure, this is volume, and it's equals to this. Okay, so once you have an understanding that work done is the same as pressure times change in volume, so that means this is true. But dimensionally, you can also prove this to be the same. What do? You begin to break this down into dimensional physical quantity, and this all into dimensional physical quantity. By breaking, saying pressure is force over area, you already know volume. This one, we have just finished this one to be N, that is force, per meter, that is length, per degree Celsius, that is T. Okay, then per what do we have? Mole, that is this, per mole. So with this, for the gas constant R, you can go ahead, you will still get it to be there. But already, we have already seen that, yeah, that is true, that it is actually equals to that. Then 1 minus 2. They also ask us to show that this entire expression here is equal to energy. Yeah, that is true, because energy and work done, they share the same unit. Energy and work done shares the same unit. So that means definitely, since this is pressure and this is volume, and pressure times change in volume is work done, then that means work done equals to what? Energy, because work done and energy share the same unit. So with that, that one is also done. Then I go to the last one. Okay, 1 minus 4 of that particular question. What did they say we should do there? Let's try to see the kind of thinking they want us to do that there. 1 minus 4. Okay, look at that 1 minus 4. Okay, what does it say? It says determine the specific heat capacity of the gaseous substance in terms of MLT, mass length time. Determine the specific heat capacity of the gaseous gas, okay, in terms of MLT. Now, you remember that there are all kinds of energy, forms of energy. We have thermal energy or heat energy, which is MC change in theta. Mass times specific heat capacity, in this case of the gas, which is what they are asking us to find, and then change in temperature. And you also know that empty energy is certain as work done. Work done, which is force times distance, or pressure times change in volume. So for them to tell me we should derive the unit, or me to express that specific capacity in terms of MLT, it means they were simply asking us to equate this to any of this, because both are energy, heat energy, work done, they are expressed in joules. So it means that I will now say MC delta theta give me P delta V. You see that? I'm looking for C. I will make C subject to the formula. Then it will be pressure times change in volume over M delta change in temperature. That is temperature. Now, this is force over area. Dot volume is L cube. Let me just write it there. Change in volume divided by this is mass. After letter M, the dimension for mass is this. Then this is temperature. Temperature is theta. Now, this one is mass times acceleration force. So we have mass is capital letter M. Acceleration is L over T squared. Okay, dot, this is volume L cube. We have mass here. You see that? M. Then the symbol for this is this theta. Okay? Now, what do we do now? Let me clean this so that I can have space to find my C. Now, with this now, we now see that C is equals to, now, this is M mass dot L. There's another L there, L is per 3. This T square will come down, which is temperature, T squared, which is time, sorry, time. Okay? Then we have M down here, we have temperature here. So this gives us what? So we have all this now, and now this is M, L raised to the power 4, divided by time squared dot M dot theta. Okay, so from this now, we can write the dimension. So you see dimension, okay, you see what the dimension you are asking for. So that means we are done. So this cancel this. Okay, so we have N raised to the power 4. M does not exist. This up, that will be T power minus 2. Then this is theta power minus 1, which we take it up. This is what the essential will write. So the dimension for specific heat capacity is this. Remember, the unit, the base unit for specific capacity, it used to be joule per kilogram per degree Celsius or Kelvin. It means that if you break this up dimensionally, it will give you this. That's what it means. Because this is the dimension of specific heat capacity. Okay, joule per kilogram per degree Celsius is the SI unit for specific capacity. And the dimension for specific capacity is this. It means if I break this down, you can try this. Joule, joule is energy. Try to break it up, you will definitely arrive at this. So with this, we have come to the end of this particular communication. View it, see it, and let us have your comments. Bye.